So now we'll move on to section 3-2 of the text. We're going to just look at some examples of applying these techniques we talked about previously to curvilinear motion. All right, so that's our goal, Newton's second law for curvilinear motion problems. And the thing to point out is that there's nothing new in this lecture. It's just applying the same things we've been doing to get some more practice for applying Newton's second laws to curvilinear motion problems. So I've got three examples. The first one is the trajectory of a golf ball. So we've done many problems for years now where you've got some projectile in a gravitational field, and we see that it follows a parabolic trajectory. Well, that assumes there's no drag forces on the body. We just assume gravity acts on the body. But if we're in air, then the air slows down the motion, and that affects the trajectory, and therefore there's no, it's not a parabolic trajectory. It's slightly modified by the drag. So that's what we're going to do. We're going to see how drag forces affect the trajectory of a golf ball in this case, or any other projectile. So we model the golf ball as a point. We use a XY coordinate system, I and J, so that gravity just affects the vertical motion. But now, if the ball is traveling this way along this unit vector UT, then the drag force will directly oppose that motion. So whichever direction the ball is traveling, the drag force acts in the opposite direction. So its direction will change as the ball's direction changes. So we use theta to denote the angle of the trajectory relative to the horizontal, and that's determined by the xy components of the velocity. We're just going to write equations of motion on this, and then we'll solve it numerically. You can't solve these equations analytically. They're too messy. So we just sum forces in the x and y directions. In the x direction, there's a horizontal component of the drag force, and then that provides a horizontal acceleration. In the y direction, there's a vertical component of the drag force plus gravity, and that gives you acceleration in the y direction. We'll assume that the drag force is proportional to the square of the velocity, speed actually. So the magnitude of the drag force is some drag coefficient CD times the square of the speed. And this is not exactly true. If you do measurements on drag forces on a golf ball, it won't be exactly v squared. It'll usually be some other exponent, but this is good enough just to get a sense of the effect of drag forces. So we can write the kinematic equations. The accelerations can be written in terms of the second derivative of the positions. The speed can be written as the square root of the sum of the squares of the speeds in the x and y direction. And the trajectory angle can be written in this way. The cosine of the angle is the x component of the speed divided by the magnitude of the speed, and the sine of the angle is the y component of the speed divided by the magnitude divided by the speed itself. Okay, which we can write this way. So this lets us take these equations, and instead of having them in terms of theta, having them in terms of x dot and y dot. So we do those substitutions, and we get these two equations of motion. Mx double dot can be written as minus CD times x dot times the speed, and y double dot looks similar. And so this is two second order differential equations for they're coupled, and they allow you to determine the x and y position as a function of time, the speeds as a function of time, the xy components of the speed, and from that you can calculate anything you want, including the trajectory. And as I said, these are too ugly to solve analytically, so we do that numerically. So if you check the dimensions, these are correct. Everything looks good. So if you take typical values for a golf ball and something hit by a driver that Tiger Woods hit, then you can get initial velocity, initial angle. We have the drag coefficient from measurements, and we have the mass of a typical golf ball. And you can just plug those into something like MATLAB and solve those equations numerically, and you get trajectories like this. So we plot the y position as a function of the x position. Without drag, we get out here to what? Something like close to 900 feet in terms of the horizontal distance traveled by the ball. If we add in drag, it's a little over 800. So we lost well over 50 feet just due to the air resistance on under typical conditions. Okay, the next example is a car traveling on an oval track. So in this end of the track, we're traveling in a circular arc, and there's some friction needed to keep the car on the track. And what we do is we bank the turns of the tracks so we can go faster without slipping. Okay, so angle theta is the degree to which this thing is banked in order to try to hold the car onto the surface. There's a friction force that acts down that bank, and if we slip, then we slip off. Okay, there's a normal force, and then there's gravity. We'll look at a coordinate system UN, which is radially inward relative to the circular arc for the path taken by the car, and B is the vertical coordinate. And there's also coordinate out of the page from this point. We'll call that T later, but we won't really address it. So we use a typical real track. So 1100 feet is the radius of curvature of this arc. And the bank angle is 33 degrees. The coefficient of static friction for the car is 0.9. And the question is, how fast can we go without slipping off the track? Okay. So we just sum forces in the N, T, and B directions. In the T direction, which is out of the page, we just assume the car is traveling at constant velocity, so there's no acceleration, so there's no force ignoring losses and friction in the car internally and that sort of thing. We just ignore that out of the page altogether. So we assume we're traveling at constant velocity. In the N direction, that is radially inward, there's a frictional component, a normal component, and that gives you this direction, acceleration in the N direction. And vertically, there's gravity, a normal component, and a frictional component, and that gives us the vertical acceleration. Now, we'll assume we're not moving vertically, so we'll assume that AB is 0. F is friction force. It's just mu times N. We ignore this T direction out of the page. And then since we're moving in a circular arc, AN is the square of the speed divided by the radius of curvature. So this gives us 7 equations and 7 unknowns. We can solve those. Turns out the acceleration in the N direction is 120 feet per second squared. The frictional force turns out to be 83 feet per second squared meters, right? N turns out to be 92.4. And then, not meters, times M. We didn't find the mass of the car, so we don't know the force, but it's 83.2 times M will give us that force. So F is 83.2, N is 92.4 times M. We can just eliminate M from that, and we don't have to know the mass of the car. So putting this all together, we find the maximum velocity allowed without slipping is the square root of rho g times this big ugly square root, which gives us 363 feet per second or 248 miles per hour. All right. So everything looks correct dimensionally. It'd look better if we knew the mass of the car, but we don't have it. The value for F is positive, so that's good. And the velocity, the maximum velocity to avoid slipping is of the order of what they drive or somewhat above what they drive in an actual race, so it seems quite reasonable. All right, let's look at one last example. This blue thing is meant to represent a solid cylinder, a hemicylinder actually, a half a cylinder. And at the top of that we place a little ball and we give it a nudge and let it fall down the cylinder. And we ignore rolling and we ignore friction. So there's assumed to be frictionless contact between the sphere and the cylinder. And at some point as it falls, it'll go fast enough that it'll just fly off the cylinder. So the question is, at what point, at what angle theta, does it separate and come off the cylinder? Okay, so we can model the surface of the cylinder here. There's a normal force, there's gravity. We have a coordinate system where r is the radius of the measured from the center of the cylinder, and so it's the radius of curvature of this surface, and u theta is the tangential direction. We just write our force equations and then solve for the angle theta at which n goes to 0. When n goes to 0, that's when the ball is starting to separate. So the radial forces are n minus the gravitational component in the radial direction. That gives you radial acceleration. Tangential is just gravity, gives you a tangential acceleration. All right, we don't need force laws here. The kinematics involve writing the radial and tangential accelerations in terms of r and theta, and we've seen that before. So we just write this down. AR is r double dot minus r theta dot squared. R double dot would imply that the ball is moving radially relative to the surface of the cylinder, and it's not yet. At some point it will, but not for the part we're interested in before separation. So r double dot is 0, so AR is just minus the radius of the cylinder times theta dot squared. And A theta, r dot is also 0, so this term goes away, so A theta is just r theta double dot, and r is the radius of the cylinder. So we can substitute the kinematics into the force balance. So we get n minus mg cosine theta is minus m r theta dot squared, and g sine theta is r theta double dot. Now to simplify this a little bit, we can write theta double dot in terms of theta dot. So theta double dot is d theta dot d theta dt. And this is theta dot times d theta dot d theta. Okay, and that should be g over r sine of theta from right here. So now we can integrate these things, okay? So the integral from 0 to theta dot of theta dot d theta dot is the integral from 0 to r of g over r sine of theta d theta. It's just integrating both sides of this equation. So theta dot squared over 2 is minus g over r cosine theta evaluated from 0 to theta is g over r times 1 minus cosine theta. So this gives you theta dot, the angular velocity, as a function of theta. So if you want to know how the ball speeds up as it slides off the side of the cylinder, this equation gives you that. Okay, so theta dot squared is 2g over r times 1 minus cosine theta. So if you put in any angle, you can calculate angular velocity. All right, but we know that n minus mg cosine theta is minus m r theta dot squared. So we just substitute from what we just wrote down. So theta dot squared is this. So n is mg times 3 cosine theta minus 2. And we were looking for when the ball separates. That occurs when n equals 0. So we set that to 0 and solve for theta and let theta s represent that separation angle. So 3 cosine theta s minus 2 is 0. So cosine theta s is 2/3. And so theta s is 48.2 degrees. Okay. So the units are good, and the value seems reasonable. That is, it goes, sort of a quarter of the way from the top to the side, half away from the top to the side, roughly, a little beyond that, and then separates, and that's about what you would expect. So it looks pretty good. All right, so those are our 3 quick examples of applying Newton's second law to curvilinear coordinates.